So let's start on time. Hello everyone. Hello everyone. So welcome to today's afternoon session. Today we'll have three wonderful talks. The first talk is by Karl Kunisch from University of Graz and Austrian Academy of Science. He will talk about feedback stabilization of autonomous systems by deep neural networks. The floor is yours, Karl, please.
Thank you very much, and thanks for the opportunity to talk here. My background is really on optimal control, optimization in the context of PDEs, and I'm really a novice to machine learning and about. So I had a good opportunity to listen to many interesting talks with subjects which were in part new to me. So to partially set the stage, I'm considering an optimal control problem over an infinite time horizon, subject to a nonlinear dynamical system with a nonlinearity F acting on the state and a operator B acting on the control. F at 0 is 0. L, which is typically just y square, L at 0 is 0, which makes the origin a steady state of the dynamical system. And this formulation here, in fact, is nothing but the optimal control formulation for stabilization of dynamical systems. We associate the so-called optimal value function to this optimization problem, which assigns the value of the minimum as a function of the initial condition. So at first, it's maybe not a priori for somebody who has no the field, what's so useful about this and function, I'll explain in a moment. Let me first recall, because it has been mentioned in several talks, that this value function under regularity assumptions is a solution to the so-called Hamilton-Jacobi-Bellman equation, which is spelled out here. And of course, this equation is to be a value at the left-hand side, which may not be simple in case the constraint contains constraints. But if U is unconstrained, we can just by hand calculate the minimizer, which is given here, and then stick the minimizer into the HGB equation, and we arrive at this hyperbolic equation in the unknown x, hyperbolic equation for the function v, this equation. It has dimension given by the state, the dimension of the state of the dynamical system. So if this is an ODE in dimension n, this is a hyperbolic equation in dimension n. If it's really just a symbol for a PDE, then we have an operator valued hyperbolic equation. What's so important in the context of optimal control is the following. If we have the function u star v, we can obtain a formula for the control in feedback form, namely, we stick in y at t and close the loop in the first equation. We really need to distinguish between open loop control, where we consider this as nothing but an optimization problem for the variables y and u, and closed loop control, where the control is expressed as a function of the state variable. Once we have it, we can take this function, plug it in here, and do what's called close the loop. To continue on this, let us, as a special case, look at the linear systems with quadratic cost. Then, under stabilizability and detectability assumptions, which are assumptions A, B, and D, this algebraic Riccati equation will have a solution. Once we solve for it, we can get the optimal control in feedback form. And here is the closed loop that I was talking about earlier. From the applications point of view, many people, many researchers, many applicationists, also for nonlinear system, would linearize the system, linearize the nonlinearity f, get A, it's a linearization of f, and then compute. And many times this approach is feasible, and then it needs to be justified, at least locally. And that's what can be done in certain cases, and which has been analyzed quite a bit. Now, to solve and to go back to the HGB equation, here are some techniques how to solve. One approach is, of course, to try to solve it directly. And we know that we are confronted with the curse of dimensionality. We can train neural networks, I'll talk about it, and has been alluded to before. Or we can use tensor train calculus techniques. We can interpolate from open loop data, as Dante Calise has explained earlier. This week, we can do Taylor explanation to get some insight, and this has been analyzed for decades now. Then there can be techniques based on Hopf formulas, which I consider interesting if they are really applicable. Their use is somewhat restricted. Max Planck algebra techniques are worked on, and more recently, tree structures. Now, before I embark into the work on training neural networks, let me ask the question, is it really worthwhile to solve the HGB equation in the first place, or is Riccati so powerful that we, in practice, cannot achieve so much more? For that purpose, and here I mentioned briefly some joint work with Dante Calise and Sergei Dolgov. Let us take a specific situation of stabilizing the Newell-Whitehead equation, which is spelled out here, by applying in the spatial dimensions -1, 1 over the time horizon 0, infinity, with a controller acting on a subdomain little omega. And the control variable is the amplitude of these characteristic functions. Together with Neumann boundary condition, this system has 3 steady states, namely 0, which is unstable, and +-1, which are stable equilibria. Now, in the following slides, we are going to look at some results where the initial condition was just constantly 10. So what do we expect? We expect that it's difficult to stabilize to 0 because the trajectory has to go through the stable equilibrium. And if there is no control, it will be just captured by the equilibrium and stay there. And then it has to be, if we control, so we pass through the stable equilibrium, we get into the neighborhood of the origin, but it is unstable. And we still have to keep it there. So let's look what we can do. What do you see on the left? As a function of time, you see the state. In gray, you see the unconstrained state. It starts at 0, and tends towards 1. Okay. We are not too surprised. Of course, the corresponding cost is infinite. Then we look and linearize and do we do a linear quadratic regulator, a Riccati approach. It tends to 0, the corresponding solution, at an extremely high cost of the control compared to HGB feedback. HGB feedback, after discretization of the PDE, to get high-dimensional ODEs, 14-dimensional ODE, we solve the HGB, we nicely tend towards 0. Higher dimensions of approximation, we go to 0 more perfectly. The cost of the control is much cheaper than the LQR approach. Now, what did we actually do? Quickly, what we did to get these results. In one word, they are based on tensor train calculus. A little bit more details. Number one, we do, I would call it a Newton approach for the HGB equation, but really more frequently people use the word policy interaction. We do a Chebyshev polynomial ansatz for y, so of course a mesh-free ansatz. We expand the value function to Legendre polynomials, we exploit separability and then tensor train calculus to get these results. Tensor train calculus is a powerful technique. Let me look how, for example, the tensor train rank behaves as a function of dimension. It is really a linear behavior. The iterations here are the policy iterations. Here it must be said, as the dimension grows, in fact, the number of needed iterations increases typically faster than linearly. And on the right, you see some graphics explaining the behavior as if of the CPU time, which and the error as a function of the dimension of the approximation. We also computed in dimension 2 and solved the HGB equation approximately with degree 121. In fact, for the linear quadratic case, one can give some bounds on the tensor train rank and then get an estimate on the number of variables which are indicated here, where R is the tensor train rank, N is the dimension of the ODE system, and N is the dimension of the expansion of the value function. So yes, the answer to this first part is that it is worthwhile to study the nonlinear version, not just always try to do the Riccati approach. Now I turn to the neural network approach to optimal feedback control. I repeat the problem under consideration. And since we are also interested in some analysis, let me say that I consider the state space W infinity for this problem, which is the space of all functions in L2. Derivative is also in L2. Functions who live in this place have the property that y tends to 0 as t goes to infinity. So those are the functions anyway that we are interested in. We want stabilization. We want a feedback mapping F star acting on the state to give us the optimal control, and we have already heard that this can be expressed by the gradient of the value function. We want to get this on a compact subset Y0 of the spatial domain, which contains the origin. So that's why we call the approach semi-global. Roughly one slide of all the assumptions. I'm sorry, I don't want to spare them. We want the gradient of f still to be Lipschitz continuous on compact subsets of the domain. F at 0 is of course 0. We want that there exists a feedback mapping from Rn into Rm such that the induced Demitzky operator acts from W in 0 in W infinity to L2, and so that the corresponding closed loop systems admit unique solutions in W infinity, and that there in fact exist optimal state control pairs of our optimal control problem. So of course, one knows how to analyze this situation, but these are the standing assumptions. The Jacobian of the feedback mapping should be Lipschitz continuous. Then there should be a bound on a neighborhood of this set Y0, such that this ensemble of solution mappings is well defined and continuously differentiable and bounded. So this is the general set. All right. I step forwards towards explaining the learning. This is the original formulation, almost, but everywhere where you saw a U on the first slide, now I stick in the feedback mapping calligraphic F as a function of the state. And calligraphic F, I'm looking for in the space of Lipschitz continuous functions. there exists at least one solution to such a problem, which is given by the gradient of the value function of the HTB. Here I formulate the learning problem on the basis of just one initial condition. Well, that is not going to do the job at the end, right? On the other hand, let me recall that due to the Bellman principle, we really learn already all along this trajectory, y of t, right? So whatever the domain of the feedback function here is already this set S for just one initial condition. So I'm not going to analyze it whenever we go on a sample later on. I'm not analyzing how to optimally sample, but at least we should bear in mind that the dynamic behavior due to the nonlinearity F will have a lot of influence how sampling should be conducted. The nicest nonlinearity would be such that trajectory is a space-filling mapping, right? Then we really get away with very few initial conditions. But in general, we meet many more initial conditions, as I have indicated here. We are going to average over them. And more generally, let us introduce a measure on y0 so that y0 is makes together with the measure is a complete probability space. And this eventually is the learning problem which we propose to solve the optimal feedback. So this is a formulation which is where the HTB equation is now steps into the background, and we in fact circumvent solving it, the HTB equation directly. I should not forget to mention that of course on Tuesday we had a talk by Mr. Rudotto, who was following a similar approach for related problems. One thing we can prove is that T admits a solution and that we have equivalence to these ensemble solutions to measure almost everywhere solutions of the original problem for each single, for almost every initial condition in y0. Now, to solve it, we need to approximate F. And here, of course, is where neural networks come in as one possible choice. So a recap on neural networks. I'm not going to go through the details. You are much more expert than myself. Just to set the notation, W I x plus B I are the affine, is the affine systems. Sigma is the activation function. We need it to be C1. It's important to realize that our feedback functions satisfy a boundary condition, namely f at 0 should be 0. So we are going to impose this on the neural networks functions by subtracting the value of this network at 0, so that the resulting networks satisfy the boundary conditions. And certainly, if we don't do that, we have much more difficulties numerically than, much less difficulties than we would have otherwise. Before I go and do some analysis, let me show some numeric, first something on the conversions. We are going to use the following universal approximation theorem. For let eta 1 and eta 2 be two scalars, which have serve the purpose of putting bounds on W1 and the shifts BI. And let's assume that the activation function sigma is not a polynomial. Then, for any epsilon, there exists a number L, which indicates the number of layers, and an architecture such that the function f star, the optimal feedback function, can be approximated in the C1 norm by the bound epsilon on the ball that we are interested in, 2m0. So, okay, if neural networks do in the C1 sense, do the job under in the situation where we can in fact put constraints on parts of the coefficients at least, namely W1 and all of the PIs, then that's one choice we can take and start to do some computations before I return to the analysis. The computations, we need to create some data. We do this for t sufficiently large. Okay, not infinity, but we have good techniques how to solve open loop optimal control problems on large time horizons. We take a regularization of the ReLU activation function. We add residual connections to our functions fi. We sample uniformly on y0. We do a gradient descent with a Barzilai-Burwein line search for optimization. And in fact, in practice, we ignore constraints. First, just to be sure, the most simple situations first, the linear quadratic case. Let's stabilize an electric network, okay, where the system matrix A has eigenvalues 0 and 2 complex eigenvalues. Okay, so it's of course an unstable system here, and we control just by some current here. And here, visually, there is absolutely no difference between the neural network approach and the linear quadratic regulator, both for the state as well as for the feedback. And the feedback gains, the optimal ones, are given on the right here, and the network parameter, which we used only single layer here, of course, are really also very close. So in this case, it works well. Let's go to another example, still very low dimensional, to a van der Pol-like oscillator, where we add a cubic nonlinearity to make it more challenging. We train the neural networks by 10 training initial conditions. We validate for another 10 conditions. The depth is 3, all the inner matrices have dimension 2, the time horizon for creating data is 50. All right. Now let's look at the results. First, these results in IW Y1, Y2 space. So displacement and velocity of this oscillator. For the van der Pol oscillator, let us recall that it has an orbit, a stable orbit. The origin is unstable, of course, again. So the first thing we see here is for different initial conditions in blue and red, at the moment they have not the meaning of training and validation yet, the orbits go along until they find a manifold where they escape. Another one and they escape. No control. Now let's do a linear quadratic regulator feedback. And we see that for some initial conditions, namely for those which are close to the origin, the linear quadratic regulator stabilizes the system. But if initial conditions are too far away from the origin, then again, they diverge to infinity. So now we do the neural network approach. We use the blue initial conditions for training and the red ones for validation. And we see that the neural network really stabilizes them all. All right. We go to Viscous Burgers equation, and we do it in dimension 14. We work in dimension 14 for the approximation of the Burgers equation by a spectral approach of a 14-dimensional ODE. If you look at the table, you see infinities which indicate divergence and you see infinity stars, which means the trajectories converge, but they converge to something incorrect. They don't converge to the origin. Okay, so for different initial conditions, without control, many times you see divergence, sure. The linear regulator, okay, it depends on the initial condition. But it many times, again, it diverges. Then another higher dimensional approximation, it diverges again. The neural network in this situation, it never diverges. So neural network does a good job in the sense we would have expected. Let's go to proof, to give some analytical validation of what we were doing. Number one, first, under proper conditions on the linearized state equation, there exists an epsilon such that the closed loops, closed now by the feedback operator based on the neural networks, they allow unique solutions and they are epsilon close to the optimal solutions based on the optimal network. Okay, this is not so obvious because the feedback functions a priori, they don't have the nice properties that the original functions would have, right? So there is quite a bit of work to do. We basically use implicit function theorem type techniques to verify this. All right, number one. Number two, now we set up the optimal control based on the network approximation. Okay, this is almost the previous formulation, just with U replaced by F theta, but there somehow we want to guarantee, we need to guarantee existence of the solutions to this problem. How to guarantee solution? Number one, we have some explicit bounds on parts of the parameters, and we have penalty functions on the remaining ones. But the penalty parameter alpha r cannot be not large or arbitrarily large, because otherwise you use our initial problem. We need to have this go to zero, as depend on epsilon, and epsilon needs to go to zero as we take the network to infinity. Now, under these conditions, the approximating problems admit global minimizers. If the regularization parameter is appropriately sent to zero, what about the convergence of the neural network approximated optimization problems to the original one? They converge from above, of course, and they converge with a certain rate. So in particular, we have convergence of the value functions, the J. It is much more delicate to have the controls and the states converge. So to make things a little more compact, I here take the situation where the measure is really a finite measure on the initial conditions. Then I choose, as epsilon k goes to zero, pairs of optimal parameters and optimal states. Then each such sequence admits at least one weak accumulation point, and these accumulation points, they do the right thing, okay? Each one of them satisfies the bounds, and they converge to the state equation, and they converge to minimizers. This ends this part, and I would like to just say that the appearance of HGB equations is not only in the context of optimization and optimal control, but it also appears in observers. In all of the above, I have assumed that I can look at my state that I then feed back. And optimal observers would be a natural next step. Another very natural next step is robustness. So they have the Hamilton-Jacobi-Bellman equation. So to make a quick summary, Hamilton-Jacobi-Bellman equations in the context of optimal control will remain to be a challenge for some more time to come. With that, I thank you for your attention. I conclude my talk. Thank you very much.
Okay, thank you very much. So is there any questions in the lecture hall or on Zoom? I do not see any questions. Maybe if that's the case, Carl, can you do you want to take 1 minute more to talk about the last part you speak over, like the observer equation?
Well, if you give me if you allow me, then
yeah, sure.
But yeah, I don't want to. I don't want to enforce myself on you. Okay. So I take 3 minutes.
Yeah, sure.
Okay. Okay. I need to set the stage. So what is the situation? We have a dynamical system. We know the structure of the dynamical system. We know there can be some noise, but all we can observe is a part of the system called Y through the matrix C. Okay? We don't know the initial condition either, right? We would like to reconstruct the state. Okay, so that's the set. Now we look at V and W as noises. So how well, but you can look at these as noise, but also as an error, how well the system, how well the equations are fulfilled. So we put them into a cost. And if we don't know anything about the initial condition, we forget this term. If you know a little bit, stick it in here for the sake of balance, right? And then first we are looking at this problem here. All right. And then we solve this problem as a function of psi. Now note the optimal control problem, the initial condition was the extra variable. Here it's the end condition. All right. We are looking at these value functions, and the minimum norm with respect to psi is what's called the Morton observer. Once we have it, we can reconstruct the state. And in one word, if some of you know what the Kalman filter is, that's a nonlinear version of the Kalman filter. All right, I did it for fixed time, initial terminal time. If we do it for all times, we get the observer. All right. Now we cannot compute it yet. Again, we need the value function. And again, the value function satisfies an HGB equation. I have written it down. Okay, I don't go through the terms, but you again see something quadratic, some affine time dependent. Now, instead of an initial terminal constraint, you have an initial boundary condition for the observer equation. All right. Mm-hmm. And again, what I'm going to do in this training it, I'm going to replace from here, wherever you saw a V before, I'm putting in the network parameters. All right, okay. And so in a sense, and now we approximate, again, by neural networks, these functions H. Okay. And this is jointly with Tobias Brighton. We tested it, and first, of course, we tested and compared to a linear quadratic situation where we can compare with the Kalman filter, and we did this for various in the dimension of the terminal conditions. And okay, the better, the more terminal conditions, the better there is the training, the smaller there is the error. So that's consistent. There is something else. This is not so good yet, okay? And this is much better. So what's the difference between these two columns? In the HGB equation for the optimal control, I insisted that we need the boundary condition for the structure of the network. If I quote, forget this boundary condition, the network, training the network is not so good. If we do something equivalent, which is not so easy in this case, the boundary condition, then again, the network does a good job. It's like 1% error, roughly speaking, which is reasonable. And once we had this for the linear case, we started with nonlinear situations like damped pendula, and well, it does is simply, I can say, it does a good job. We go to this, we detect the orbit, and that's what we want. I don't want to go into details, but these are the training orbits, and here we test, and it does a reasonable job. It depends. Here we were, this one thing is we were pretty close to the training set. We are going further away from the training set. It has some difficulties at the beginning. So that was the other part. Thank you very much for the extra time.
Yeah. Thank you very much for the interesting introduction of the observer problems. So maybe now, can you unshare your screen and let the second speaker test the sharing? Oh,